Hello, it's Keith here, and this is lesson 34 of the simple series of my Z80 assembly programming tutorials, and we're back on the Sega Master System, also the Sega Game Gear, basically the same thing for the intent and purposes of today. We're looking at a simple bitmap routine, and this time we've added sprite clipping. Now you see we had the example before where we had our Chibiko mascot moving around the screen. We're using the Tilemap to draw this bitmap today, but now our graphic can go off the screen partially or entirely, and we're doing some clipping to work out when to remove parts of this graphic. Now today we're just using the Tilemap, so a very simple way of getting graphics onto the screen. We're going to look at Hardware Sprites next time, so don't think that I'm sort of letting you down there, but say if you're just getting started with writing a game, being able to use the Tilemap I think is a nice easy way to get started, so you don't have to worry about hardware sprite numbers and things like that. So that's what we're going to be looking at today. First of all though, we need to discuss the theory because there's some various things we need to discuss here. Okay. Now, this example is being ported to all of my different systems on the Z80 6502 and 68000, so we need a way that works commonly on all systems, and so we have an issue of coordinates. A lot of our systems are 256 by 192 in size, some are a bit bigger as well, but we want to work with a single byte XY coordinate, and so I use a logical unit system where basically one logical unit is 2 physical pixels. Now on the Sega Master System in tiles, each tile is 8 by 8 pixels, and so that means each tile is 4 by 4 logical units. So that's how I'm calculating my coordinates, and that's what I'm tending to use these days on all of my systems. It's a nice easy way of calculating coordinates, and it gives me the flexibility that I need to work with all of these different systems in a common way. So that's what we're doing there from a coordinate point of view. So now what we need to discuss is the actual way that I'm calculating the cropping for this algorithm. So basically, as I say, I'm basically using the same thing on every system. So if we've got our screen here, this big box here, and if this thing here is our sprite, there it is, there's our sprite. Our sprite will move around the screen, and our sprite is made up of 8 by 8 tiles. So our sprite today, our graphic is 48 by 48 pixels, and so that's 6 by 6 tiles, and so it's a grid. Now when our sprite goes partially off the screen, we're going to have to alter what we're drawing to the screen. So in this case, where the sprite has gone off the top of the screen, we're going to need to change the height of the sprite to this amount. The drawing position is going to have to be reset to 0, and we're going to have to skip the tiles that make up this part of the graphic. So that's what we would need to do if we go over the top. It's different though if we go over the off the bottom of the screen. Now we need to change the height, but we don't need to skip anything because we'll just give up before we get to the tiles we need to remove. On the left hand side, well, we need to do things a bit differently. We need to change the X position, of course, and change the width of the sprite. We need to skip some of the tiles before we start drawing at all. We're drawing in a zigzag pattern on all of these systems, so we would need to skip these first few tiles here before the first line. But then after each consecutive line, we would need to skip these tiles as well. That's on the left-hand side of the screen. On the right-hand side of the screen, well, it's different again. We would need to change the width, and we would need to skip tiles after each line, but the first tile would be the first thing we draw. The final thing, of course, is, well, it could be off multiple sides, so we might need to do some permutation and combination of these. And the original Chibi couldn't do it correctly. The cropping algorithm, which took me about 2 weeks to write, didn't work even after those 2 weeks because I was a terrible coder, and I'm still a terrible coder, but I'm a slightly less terrible coder, and so we have an algorithm that hopefully works correctly today. So here it is. This is the example for today, and as I always say, you can go to my website and you can download it and you can do whatever you want with it. You tear it apart, right? Make better versions, put it in your own programs, even if they're commercial. Good luck to you. It's what it's there for. So hopefully it can be some use to you. So we're not going to look at the stuff that hasn't changed. It's based on the original simple sample examples, the bitmap example and the joystick example. We've just extended it with this new version of the draw player routine. So this is the new version. We are passing the X and Y coordinates in B and C. These are now all in logical units, and we're specifying the width and the height in logical units, not tiles. So 24 by 24 logical units is 48 by 48 pixels. IY is specifying the first tile number of the top left corner of the graphic, tile number 128, and we're then calling our do crop routine. This will do the cropping, and it will set the carry if the sprite is entirely off the screen. And I have this sprite stick for the purpose of the example. So if our sprite is completely off the screen somewhere, nothing to draw. If it comes on the screen, there's something to draw. So we're using the carry for that purpose there. And if the carry is not set, we'll run the fill area with tiles routine, which is actually down here. So I guess maybe I could have read those two lines out, but for clarity, they are there. Okay, now at the very start of our code we are defining a few things. We are defining the position of the top left corner of the logical screen here, so at pixel position 6480 in logical units, and you can see that just here. So that is the first visible pixel in logical units. We're specifying the width and the height in logical units as well. 128 by 96, remember, pixels divided by 2, so 256 by 192 divided by 2 is 128 by 96. So that's why we're doing that. We're also doing a few other things. We're defining a byte of data for the visible screen bank. We're using a double buffer to stop any screen flickering here, and we'll discuss how that works in a moment. And we're defining a sprite h-clip byte here, and that is being used for the cropping, because as I said before, if our sprite is off the left or off the right, we're going to need to skip a few tiles before we draw the next line, and so that's what that's going to be used for. Okay, let's see the cropping algorithm then. So down here, here it is. It's pretty much the same on all systems. There's just a few tweaks here and there for the peculiarities of the system. So on this system, we are starting off by zeroing the sprite h-clip. We're setting it to 0. We'll set it to something else if we actually need to clip the left or the right when we get to that part. D and E are being used as temporary variables throughout this routine, and B and C are our X and Y position, and H and L are our width and our height. Okay, so the first thing we're doing here is we're taking our Y position in logical units and we're subtracting the minimum logical coordinate of the first line of visible pixels. And so what we've got to think of is if our sprite is somewhere like this, this will now change the accumulator to a negative value because we are below 0 once we subtract that first line. Now in that case we're going to need to do some work, but otherwise we would just skip. If we've not off the top of the screen, our sprite must be entirely on the screen or somewhere else that we need to deal with. Maybe it's completely off the bottom of the screen. We'll deal with that in a moment. So we're going to convert that negative value, if we're partially off the top of the screen, into a positive value, and then we're going to compare it, after converting it to a number of tiles, to the height of the sprite. Now you see, if the sprite is entirely off the screen, this will be greater than the height of the sprite, and in that case we're jumping to all off screen. All that does is it sets the carry and returns, so that's our give up routine effectively. Okay, so that's what we're doing if we're entirely off the top of the screen, but if we're not, then we're storing this value in E for later. That's the amount removed from the top, and we're setting A to 0, and that's because A is the new Y position of the sprite. Still in logical units, we'll convert it later, but it's a bit closer to the final value there. So that's what we're doing. What we're doing here is we're going to now consider the sprite related to the bottom of the screen. So we're going to deal with any cropping at the bottom of the screen this time. So we're adding the height of the sprite, and then we are subtracting the height of the screen. Now if this is still a positive value, this means our sprite must be somewhere like this, partially off the bottom of the screen. So again, we're converting to a number of tiles and comparing to the height of the sprite, and if it's the entire height of the sprite, that sprite's all the way off the screen, so we give up, but otherwise we store the amount removed from the bottom in D. Okay. By this point, we've now got the amount removed from the top, if anything, and the amount removed from the bottom, if anything. So we're adding those two together, and if it's not 0, we're negating it to give a negative value, and we're basically subtracting that cumulative value from the height of the sprite, and we're updating the new height of the sprite there. Okay, so that's the height of the sprite adjusted, but now what we're going to do is we're going to use the E register, the amount removed from the top, and we're going to use this to update the first tile number. What we're doing here is we're taking the width of the sprite in logical units and we're converting that to a number of tiles. What we're basically going to do here is we're going to remove the number of tiles for each strip of the sprite if our sprite's off the top of the screen. If our Chibiko is off the top like this, well, we need to remove the tiles that make up the head there. So that's what we're doing here. So we're just calculating the amount of lines to remove, calculating the number of tiles per line here, and then we've got a very simple loop here, very simple multiplication, effectively updating the IY tile number for those lines. Say it's not very efficient multiplication here, but you've got to bear in mind this routine won't run at all unless our sprite is cropped, and it's only going to run once per frame as well. So it's not going to be a major consumer of our processing power. So I don't think it matters that it's not very efficient. Okay, so we've done the y-axis. We're going to now do the x-axis, and we're going to do the same thing again. So we're resetting DE here, and now we're going to do the same for the x-axis. So we're loading the x position, and we're subtracting the minimum x. And so what we're doing here is we're basically considering our sprite and comparing it to the left like this. Now again, If this has not caused a carry, then our sprite must be entirely on the screen on the x-axis, so nothing to do. But otherwise, once again, we convert that negative back to a positive and we compare this time to the width. If it's more than the entire width, well, our sprite must be somewhere entirely off the left-hand side of the screen, so we would give up. Nothing to draw. So at this point we've kind of wasted our time previously because the sprite was entirely off the left hand side of the screen, but at least we don't need to draw it. But if it is partially on the screen, we're storing the amount to remove from the left in E, setting the X position to 0. Again, we're drawing from the far left. We then add the width, subtract the screen width, and once again, if this is not negative, well, the sprite must be somewhere like this, must be partially off the right hand side of the screen. So again, we're comparing to the width of the sprite, and if the sprite is entirely off the screen, if that's greater than the width, well, we must be somewhere like that. So again, we would give up in that case. Otherwise, we now have the amount to remove from the right-hand side of the sprite. Okay, so what we're going to do now is we're going to add these two together. We're adding D and E, and we're converting to a number of tiles. We're storing that in sprite hclip, because remember, whether our sprite is off the left or the right, and if it doesn't turn around, there we go, then we need to remove some tiles after each line is drawn, because as I say, we're drawing in a zigzag. And so we're storing that in sprite hclip, and we'll see that in our drawing routine in a bit. Okay, we're converting that then again back to a number of logical units, and we're updating our width. Kind of not necessary, maybe we could have converted straight to tiles at this point possibly, but I'm retaining the theory of working into the logical units until the last point here. Okay, so our width is now updated. The final thing we're doing here is we're taking the E value here, the amount to remove from the left, and we're converting this to a number of tiles, and we're adding it to IY, and this is to skip any tiles from the left hand side. So if you think of that fireball, if we're off the left here, we need to skip it, and this is what we're doing here. We're removing a few tiles from the first line, and so IY has been updated there. Finally, now we're converting all of the units from logical to physical, and we're working in tiles here, so we're effectively dividing all of these values by 4, converting the width, height, X and Y into tiles. We then clear the carry and we return, so we're now ready to draw. Okay, so that is our cropping routine. So what about actually drawing to the screen? Well, we're using fill area with tiles, which has only been very slightly changed really. We are again calculating our end positions here. We're using get VDP screen pos on each line to calculate the VRAM destination and to select it. We're then writing our IY pair, which is the tile number, and of course any other options maybe if we were using flipping and things, but just our tile number in this case. After each tile, we're increasing IY and we're moving across the screen for the next one. We are just repeating here until we've done a line. Once we've done a line, we are potentially having to skip some tiles. So we're loading in sprite hclip here into DE, and we're adding that to IY, effectively skipping any tiles for that left or right crop. That's what we're doing there. So once we've done that, we just then repeat and we do the next line. So that's the end of the drawing and cropping routines. The final thing I want to discuss is how we're doing our double buffering. We've got 2 buffers and we're toggling between them to end up with no sprite flicker as we're drawing the screen. And the way we're doing this is we've got 2 tile maps. Now each tile map is very nearly hexadecimal 800 bytes here. And so we have got 2 tile maps, one at effectively 3800 and one at 3000. And so basically we are taking a bit in visible screen bank, which will be a 1 or a 0, and we're shifting it into the correct position, ORing in 30, and adding this to our HL pair before we select our VRAM destination. And so we're here selecting our tile memory position for a tile number specified by BC, an XY position. And as I say, we're just specifying the top byte of the HL pair based on this screen bank. And the way we're using this is we've got a flip routine here. So after each frame has been done, we run the page flip, and this flips the visible screen and changes that parameter for the next execution of drawing. So our page flip is very simple. We are using VDP register 2 here. The 128 is added to it to specify that we're changing a register value. And all we need to do is we need to send a byte with all of the bits set to 1, except for bit 1, which is either a 1 or a 0. And this is specifying the screen base of the tile map. So that for the tile map to be at 3800 or 3000, we need to toggle that bit between a 0 and a 1, and if it's a 1 then it will be at 3800, and if it's a 0 it will be at 3000. So we're shifting the bit from visible screen bank accordingly. and then we're just XORing that bit each time for the next frame. And so this is toggling so that the visible screen is the last frame and the new drawing frame is the previous visible one. That's all that's doing. So this page flip routine is handling that. And we just have a clear screen routine which is using it in the exact same way as the top bit of the low nibble of this pair here, so that we've basically got our VRAM destination, and then we're just writing loads of 0 tiles to clear the screen. So there we go. So that's all we're covering today. If you've liked what you've seen, please like and subscribe, and as I say, you go to the website, download the example and use it and make something great out of it. Hope it's some use to you. Anyway, hope you've enjoyed what you've seen today. Thanks for watching and goodbye.